Welcome to Bot Thoughts by AmtocSoft. I'm Alex, and joining me as always is Sam, our resident AI systems expert. Today we're getting into something that I think is genuinely one of the most important shifts in AI right now: reasoning models. We're talking about OpenAI's O3, DeepSeek R1, and Claude's Extended Thinking mode. Sam, before we dive in, quick question. Is reasoning model just a marketing term, or is something actually different here?
It's a real architectural difference, not a rebrand. The core idea is that these models get a compute budget at inference time, meaning when you actually use them, to generate and evaluate intermediate reasoning steps before producing a final answer. Standard LLMs generate one token at a time, left to right, with no ability to revise earlier decisions. Reasoning models break that constraint by giving the model a scratchpad to think through problems, explore alternatives, and catch its own errors before committing to a response. The difference in performance on hard problems is dramatic. We're not talking about 10% improvements. We're talking about GPT-4o scoring 5% on the ARC-AGI benchmark, while O3 at high compute scores 87%. That's a different category of capability.
Okay, but wait, we've had chain of thought prompting for a while. Just telling the model think step by step. Isn't that basically the same thing?
It's related but fundamentally more limited. Chain of thought prompting works because it forces the model to externalize intermediate reasoning into the context window, so each step can condition the next. That's genuinely useful. But the model is still constrained in a critical way. It cannot revise a step it has already omitted. Once a token is generated, it's committed. And it has no mechanism for exploring alternative reasoning branches. It goes down one path and follows it to the end. So what you get with chain of thought is a model that produces reasoning-shaped text. For easy problems, that's fine. For hard ones, multi-constraint math, adversarial debugging, anything requiring backtracking, you hit a ceiling fast. Reasoning models break through that ceiling by giving the model the ability to generate private thinking tokens before its final answer, explore multiple approaches, and self-correct in a way that chain of thought simply cannot.
So what actually changed to make this possible? Was it just more training data, or is there something fundamentally different about how these models are trained?
The key change is the training objective. Standard LLMs are primarily trained with supervised learning on human-written text, followed by RLHF, reinforcement learning from human feedback. The reward signal is human preference. Does this response seem good to a person? Reasoning models shift that second phase. Instead of human preference feedback, they use reinforcement learning on verifiable outcomes. Concretely, does the code pass the test suite? Does the math answer match the ground truth? Is the logical conclusion formally valid? This is only possible in domains where you can automatically check correctness. But the bet that DeepSeek and OpenAI made, and it turned out to be correct, is that training on math and code is rich enough to develop general reasoning capabilities that transfer to other domains. And the compute budget at inference time is the mechanism that lets the model actually use those reasoning capabilities when you call it.
Let's talk about DeepSeek R1, because I think a lot of people in the developer community were genuinely surprised by that one. This was an open-source model from a Chinese AI lab that showed up and matched or beat closed models from OpenAI. What was actually happening there?
DeepSeek R1 was a landmark release for two reasons. First, the performance. On coding and math benchmarks, it was genuinely competitive with O1. Second, and more importantly for developers, DeepSeek published their full training recipe. That's unusual. Most frontier AI labs treat their training methods as crown jewels. DeepSeek put it all in a paper. The method they used is called GRPO, Group Relative Policy Optimization. It's a variant of PPO, which is the standard reinforcement learning algorithm for language models. But instead of comparing a response to a fixed reward model, GRPO evaluates a group of completions against each other. You generate, say, 8 different responses to the same problem, score them against the verifiable outcome. Did it get the math right? And update the model based on relative performance within that group. No human feedback. No human-written reasoning examples in the initial training phase. The model learned to reason purely by trial and error against objective checks.
That's fascinating. So the model just taught itself to reason, with no one explicitly showing it what good reasoning looks like.
Exactly, and what's remarkable is what emerged from that process. DeepSeek's paper describes a behavior they call self-correction, where the model, midway through its reasoning trace, would pause and write something like, "Wait, I made an error in step 3. Let me reconsider." The researchers did not program this in. There were no training examples of a model self-correcting. It emerged spontaneously from reinforcement learning against verifiable outcomes. When the model discovered that catching its own errors led to better final answers, which led to higher rewards, it learned to do it. That's a genuinely surprising result, and it's part of why the AI research community took R1 so seriously. It's not just that the model performs well. It's that the training process produced behaviors the designers didn't anticipate.
Let's talk about OpenAI's O3. That's the one that's been getting the most attention from a benchmark perspective. What's the story there?
O3 was the most significant reasoning model release of early 2026. OpenAI hasn't published the full technical details the way DeepSeek did, but from the O1 paper and the released benchmarks, we know a few things. It's trained with reinforcement learning on verifiable outcomes, same general approach as DeepSeek. It has a configurable budget that you can set to low, medium, or high, which controls how many tokens the model spends reasoning before giving you an answer. And the performance differences across those settings are dramatic. On the ARC-AGI 2 benchmark, O3 at high compute scored 87.5%. GPT-4o on the same benchmark scored 5%. On AIME 2024, which is competition math, the kind that stops most humans, O3 at high compute scored 96.7%. GPT-4o scored 9%. The gap isn't incremental. It's the difference between a model that can and a model that cannot.
And then there's Claude's extended thinking mode. Anthropic took a different approach to how they present this to users, right? There's something about transparency that sets it apart.
That's one of the most interesting differentiators, yes. Claude's extended thinking mode, introduced in Claude 3.7 Sonnet and continued in Claude 4, shows you the reasoning by default. When you enable extended thinking via the API, you get two types of blocks in the response. Thinking blocks, which contain the model's internal reasoning trace, and text blocks, which are the final answer. With O3, the thinking process is opaque. You see the final answer and a time elapsed, but you don't see what the model was actually working through. With Claude, you can read the full chain of reasoning. That's both a design choice and a transparency statement. For production use, it's actually quite useful. If your system produces an unexpected answer, you can inspect the reasoning trace, see where the logic went wrong, and adjust your prompt or your problem framing accordingly. It turns debugging from guesswork into something closer to actual diagnosis.
Can you walk through what that actually looks like in code? Like, if I wanted to use extended thinking with Claude right now, what does the API call look like?
Sure, you enable it by adding a thinking parameter to your messages.create call. You pass a dictionary with type set to enabled and budget underscore tokens set to however many tokens you want the model to think for. Something like 6,000 is a good starting point for moderately complex problems. The model then spends up to that many tokens on its scratch pad before generating the final response. When you iterate over the response content, you check the block type. Thinking blocks give you the raw reasoning text. Text blocks give you the final answer. One important thing to understand, the thinking tokens are billed at the input rate on Anthropic's API, not the output rate. That matters because output tokens are 5 times more expensive than input tokens for Sonnet. So a generous thinking budget costs less than it first appears. And we wrote about all of this in detail in our latest blog post. The link is in the description.
All right, so reasoning models are clearly powerful, but I imagine there are cases where you shouldn't use them. What's the decision framework here? When do you reach for a reasoning model versus a standard LLM?
The right question to ask is, does this problem require the model to check its own work? If yes, reasoning model. If no, standard LLM. More specifically, reasoning models excel at complex code generation or debugging where you're juggling multiple constraints simultaneously: correctness, performance, security, API contracts. They're excellent for multi-step planning where you need to check constraint satisfaction before committing to an approach. And they're the obvious choice for mathematical or algorithmic reasoning, where you should not use them, latency-critical applications. A 47-second thinking time is fine for a batch job. It's a deal-breaker for a live chat interface. Simple retrieval or classification, using O3 to extract structured fields from a form is technically capable but economically absurd. And cost-sensitive high-volume workloads. O3 at high compute is roughly 25 times the price of GPT-4o per output token. For 10,000 requests a day, that difference is very real money.
I love that you mentioned latency, because I think that's the one that catches developers off guard most often. You've hit this personally in production, right?
Absolutely. I was building a compliance checker, a system that takes a contract clause and verifies it against 12 specific regulatory requirements. The accuracy with a reasoning model at high budget was excellent. The problem was the P99 latency was 68 seconds. Legal review workflows can tolerate that. But I'd also wired the results into a real-time UI that highlighted clauses as the user typed. 68-second lag is completely unusable for that interaction. The fix was a two-tier system. A fast path using GPT-4o at 1 to 2 seconds. Check whether the clause is likely compliant using a simpler prompt. Show a preliminary green, yellow, or red indicator immediately. Then a slow path using O3 at medium budget, running in the background, confirming or overriding the fast path indicator. It surfaces detailed reasoning to the user in a collapsible audit trail panel about 8 to 12 seconds later. The perceived latency drops to under 2 seconds while the accuracy stays at the reasoning model level. The key insight is that you don't have to choose one or the other. Use fast models for preliminary signals. Use reasoning models for verification.
I want to ask about benchmarks, because there's a lot of noise here. Every model release comes with claims about benchmark performance, and it can be hard to know what to actually believe. What benchmarks should developers trust for reasoning models?
3 benchmarks worth trusting. SWEbench verified real GitHub issues with real test suites. No synthetic problems, minimal contamination risk. As of April 2026, O3 at 71.6%, Claude Sonnet 4.6 at 49%, GPT-4o at 38%. ARC-AGI abstract reasoning tasks that humans solve easily, but that standard LLMs consistently fail. Extremely hard to contaminate because the task format is novel. And AIME, competition math, limited public solutions, hard to contaminate. What to be skeptical of? MMLU scores for reasoning models. MMLU is multiple-choice trivia style, and standard LLMs have already near-saturated it. A 2-point MMLU improvement tells you almost nothing. Human eval is widely contaminated in training data. Use SWEbench or Live Code Bench instead. And always check whether self-reported benchmarks use the publicly released checkpoint or a separate eval model specifically tuned for benchmark performance. That's a real and documented problem in the field.
Let's get practical about cost for a minute. You mentioned O3 at high compute is 25 times more expensive than GPT-4o. How do developers actually optimize for this? Is there a systematic approach to thinking budget tuning?
Yes, and it's underappreciated. The first thing to do is not set your thinking budget to maximum and call it a day. Run evaluations at 2,000, 5,000, 10,000, and 20,000 thinking tokens. For most tasks, 5 to 8,000 tokens captures 90% of the accuracy gain at 40% of the cost of the maximum budget. You're looking for the knee in the accuracy versus budget curve. Find it, deploy at that budget. Second, prompt caching. If you're running the same reasoning task repeatedly, evaluating 1,000 contracts against the same 12 rules, for example, the system prompt and the rule set can be cached. On Anthropic's API, cached tokens cost about 10% of the normal input rate. The dynamic part of your prompt still incurs full cost, but if your system prompt is substantial, caching cuts your bill dramatically. Third, streaming. Both the Anthropic API and the OpenAI Streaming API support streaming the thinking content. Stream it to the client to show a progress indicator during long reasoning sessions. Users see still thinking with intermediate reasoning rather than a frozen spinner. It makes 47 seconds feel much shorter.
All right, let's land the plane. If someone's listening to this on their commute and wants to walk away with 3 things they can act on this week, what are they?
First, identify one task in your current system where accuracy matters more than latency and the output is verifiable. Code review, compliance checking, complex database query generation. Swap in a reasoning model at medium budget for that task this week. Measure the accuracy delta. My guess is it's larger than you expect. Second, do not assume one budget fits all. Run a quick eval at 3 different thinking token levels, 2,000, 6,000, and 12,000. Plot accuracy versus cost. You'll almost certainly find a need that saves you money without losing much quality. Third, consider a 2-tier architecture for any user-facing application that uses reasoning. Fast model for the immediate response. Reasoning model running in the background for verification and depth. This pattern unlocks the capability of reasoning models without making users sit through 40-second waits. Those 3 things, one task swap, budget tuning, 2-tier architecture, will make you a meaningfully more effective user of reasoning models.
That's exactly the kind of concrete, actionable advice we love on this show. Sam, this has been a great one. For everyone listening, if you want to go deeper on the technical details, including actual code examples for Claude Extended Thinking and the DeepSeek R1 training recipe, we have a full deep dive blog post at amtocsoft.blogspot.com. Link is in the description. If this episode helped you think about AI differently, please subscribe on YouTube or wherever you get your podcasts. And if you want to support what we're doing here at AmtocSoft, you can buy us a coffee at buymecoffee.com/AmtocSoft. Every coffee helps us keep producing content like this. I'm Alex, Sam's been Sam, and this is Bot Thoughts. We'll see you in the next one.